You've likely handled a sliced lemon, a bottle of vinegar, or a container of yogurt that's a day past its prime. You might even have a heavy car battery sitting in your garage. You know these substances through your senses. When you bite into a lemon, that sharp, sour taste that makes your face scrunch up is acid interacting with your tongue. Acids power our vehicles and provide the corrosive strength to strip rust from iron gates. Your stomach even produces its own supply to break down the food you eat. These objects share almost no physical traits. They look, feel, and function in completely different ways, yet they all belong to the same chemical family. To understand why a lemon and a car battery are related, we have to look past the surface and examine their behavior at the molecular level. In the late 19th century, a Swedish chemist named Svante Arrhenius identified the specific trait shared by every acid. Arrhenius conducted his research in laboratories like this one, studying how different chemicals react when they are dissolved in liquids. He discovered that an acid's true identity only reveals itself when it touches water. This process is called ionization. When a molecule of hydrochloric acid enters the water, the bond holding it together breaks, and the molecule splits in two. Arrhenius realized that when an acid splits, the piece carrying the positive charge, the cation, is always hydrogen. This is the definitive scientific rule. An acid is any substance that, when placed in water, releases hydrogen as a positive ion. While the rule is the same, not all acids release the same amount of hydrogen. To classify them, we have to count what they deliver to the water. Some acids, like hydrochloric, release one hydrogen ion. Sulfuric releases two. Phosphoric releases three. But we have to be careful. Acetic acid is written with 4 hydrogens, but only one actually breaks off. We only count that single escaping ion as the ionizable hydrogen. We also sort acids by their ingredients. Molecules with no oxygen atoms are called hydric acids. If the molecule includes oxygen, it is classified as an oxyacid. Finally, we look at the degree of ionization. If almost every molecule in the water breaks apart, the acid is strong. If only a small percentage divide, it is weak. In a laboratory, these labels don't measure how much a chemical burns. They measure how it behaves in water. Hydrofluoric acid is chemically weak because it barely ionizes, yet it is corrosive enough to dissolve glass and destroy human bone. Scientific classifications of strong and weak describe molecular efficiency, not a measure of real-world safety or toxicity. We can now look back at our everyday world, at the lemon and the vinegar and the car battery, with a different perspective. We are seeing a specific chemical behavior in action. Every one of these items is busy shedding positive hydrogen ions into the water around them. This shared molecular trait is why these vastly different substances are considered part of the same family. This raises a logical question. If an entire category of matter exists solely to release positive hydrogen, is there a substance that does the exact opposite? There is. It feels slippery to the touch, it can cancel out the effects of an acid, and we use it for everything from painting walls to unclogging drains. That substance is called a base, and it's the subject of our next lesson.